All right. So today we are going to continue with lecture set number 5. Lecture set number 5 is devoted to the study of the normal distribution. And in particular, our focus is on finding area underneath a normal curve, which, as we defined on Thursday, is a bell curve. An illustration of a normal curve is actually given on the current slide. So you can see underneath number 3, I've sketched out a bell curve, which is a symmetric curve that's centered about the mean of the distribution. So far, we have been learning how to find area underneath the standard normal curve. The standard normal curve is a specific normal curve where the mean is 0 and the standard deviation is equal to 1. So theoretically, we actually have an infinite number of normal curves that could be observed in practice. The standard normal curve is one of that infinite number of normal curves. And we use the standard normal curve, or rather we use the standard normal table to find area underneath the standard normal curve. These areas are actually probabilities. So by doing this, we are able to find the probability of observing a certain outcome. For example, in number 3, we wanted the probability that Z was less than negative 1.645 plus the probability that Z was greater than 1.645. Okay, so we're going to look at one more example of finding area underneath the standard normal curve. So this will serve as a refresher of what we were learning on Thursday when we first introduced this curve and the corresponding table. After this exercise, we're going to go in reverse, and we are going to use area underneath the curve to find a z-score along the axis of the curve. After that, we're going to look at 2 extensions where we can find area underneath any normal curve and where we can find a horizontal value for any normal curve. So effectively, what we are doing is we are learning how to find probabilities of an event for any normal distribution and how to find the percentiles of any normal distribution. Those are the 2 main end goals of this unit. All right, so for the last exercise, number 4, we have find the area below negative 1.85 and the area above negative 0.56. So we start by sketching the curve. Okay, so this is my normal curve, or sorry, my standard normal curve. Again, every standard normal curve is centered at 0. So the 0 will always get placed in the middle whenever we are working with the standard normal distribution. We have 2 values, negative 1.85 and negative 0.56. All right. So we want the area below negative 1.85 and the area above negative 0.56. So here we have the probability Z is less than negative 1.85 plus the probability that Z is greater than 0.56. Right. So this is the probability Z is less than negative 1.85 plus 1 minus the probability that Z is less than negative 0.56. All right, so all we have left to do now are look up the two Z scores. So we go to our standard normal table. We're working with two negative values in this case. So we have negative 1.85 and we have negative 0.56. So in that case, we're going to use the first page of the standard normal table because that's the table that gives us negative Z scores. So we'll look for negative 1.85. Here's negative 1.805. Okay, so we're going to match these columns together. And that gives us 0.0032. So the probability that Z is less than negative 1.85 is 0.0322. Okay, our second Z score is negative 0.56. So using the same table, here's negative 0.5. Here's 0.6. So that gives us 0.287. Okay. So the probability that Z is less than negative 0.56 is equal to 0.2877. Okay, so we have 0.0322 plus 1 minus 0.2877, which is 0.0322 plus 0.7123, which is 0.7445. Okay, so the probability that a Z score is less than negative 1.85 or greater than negative 0.56 is equal to 0.7445. Right. Any questions? Okay, so now what we're going to learn how to do is go in the opposite direction. So we started by taking a Z score, so a value that exists along the horizontal axis of the bell curve, and we use that Z score to find the area to the right or the left of said Z score. Now what we're doing is we're going to say, or we're going to ask, what if I am given an area underneath the curve? So instead of starting with a value along the axis, I am starting with the size of the shaded area. What Z score will make that area a specific size? That's the question we are trying to answer. So we want to know what value on the horizontal axis, so what Z score will give us whatever area we are interested in finding. All right, so this particular exercise introduces a new notation, which we call Z score notation. The Z score notation tends to confuse students. The reason that it confuses students is because they don't understand or they don't remember what the subscripted value is representing in the notation. Okay, so in general, our z-score notation can be written as shown here. Okay, so this is z, that's an S. This is z-score notation. What this is telling us is that we have a z-score, and to the right of that z-score is alpha sized area. Okay, so this is a z-score with area of size alpha to its right. So for example, suppose that we have z subscript 0.025. Z subscript 0.025 is the z-score that puts an area of 0.025 to its right. Okay, so in the diagram below, this barrier here would be z subscript 0.025, such that this red shaded part here is a size of 0.025. Right? So the subscript notation does not represent, so for example, what I wanted to say is notes. This is one value. Okay. Z subscript 0.025 does not equal Z 0.025. Okay. This is notation that represents a z-score with an area to its right of size 0.025. So whenever we see this type of notation, we are being told how much area is underneath the curve to the right of the value that we want to find. So let's consider the example that we are working with right now. So we have Z subscript 0.025. So 0.025 of the area underneath the standard normal curve is to the right or above the z-score that we want. So we want to find the z-score that has 0.025 of the area under the curve to its right or above it. So to find this value, our process is as follows. Take the subscripted value, so 0.025 in this case, subtract it from 1, and then look up the result. So whenever we want to find a z-score using z-score notation, our task is simply to subtract the value in the subscript from 1 and then look up the returned value in the table. Okay, so we are going to go to the standard normal table. We are now looking for 0.975 inside of the table because we are working with an area underneath the curve. Okay. Now we just come out to the axes, 1.96. All right, so we're literally going in the opposite direction in this case. Right. So what that means is that Z subscript 0.025 is equal to 1.96. Right, so that's the result. we found the z-score that has 0.025 of the area under the curve to its right. Any questions? Always. Yeah. Yeah, sorry, Emil, this question is, so the subscript is always the area to the right? Always. That's a definition. All right, so let's look at a few examples here. Oh, this was, sorry, I used the table. This was for the last problem. Let's fill this out. Okay. All right, so let's look at another example. So the process here is exactly the same. All we're doing is changing the subscripted value. So in this question, we're being asked, what is the value of Z subscript 0.4? All right, so that means here on this boundary line, we have Z 0.40. Okay, so the subscript represents area to the right. So this red shaded part here is a size of 0.4. That's the area to the right of the z-score that we are looking for. All right, so we take our area in the subscript, we subtract from 1. That gives us 0.6. Now we look 0.6 up in our standard normal table. So we go to our normal table. Actually, I'm just going to make sure I don't have. Okay, good. So we go to our normal table and we're looking up 0.6. Right. So we have two options in this case, 0.5987 and 0.6026. So in general, whenever we are between two values, unless we are perfectly in the middle, we just round to the closest value. So in this case, 0.5987 is only 0.0013 units away from 0.6. 0.6026 is 0.0026 units away from 0.6. So that means that 0.5987 is the closer unit or is the closer value. So our z-score is then going to be 0.25. Right. Okay, so in that case, we can write Z subscript 0.4 is equal to 0.25. Any questions? Okay, now an important point, and we're going to come back to this a little bit later. Z subscript 0.4 is the z-score that puts 0.4 to the right. That means that this white shaded part here is a size of 0.6. Okay, so therefore, what we have actually found is the 60th percentile of the standard normal distribution. So this is a size of 0.6, thus is the, so Z 0.40 is the 60th percentile of the standard normal distribution. So this is another reason that students get confused with the notation. Again, the Z subscript notation is always giving us area to the right, always, no matter what. But when we are asked to find percentiles, we're being asked for areas to the left. So Z 0.40 is the 60th percentile. That would mean that Z 0.30 is the 70th percentile. And then that would mean that like Z 0.2 is the 80th percentile. Okay, and then hopefully you can see the pattern. The notation is giving us 1 minus the percentile that is actually of interest to us. Okay, so in that sense, they're complements. So the notation is a little bit, in the case of finding percentiles, the notation is a bit annoying because you're always using the complement in the subscript, but that is how the notation works. And later on in the course, when we talk about confidence intervals, we will see the notation again. And in that setting, the right side area value makes a lot more sense. But in terms of finding percentiles, we have to keep in mind that it's always talking about a complementary relationship. So if I want the 60th percentile, that's Z 0.4. If I want the 70th percentile, that's Z 0.3. If I want the 20th percentile, that's Z subscript 0.8. Okay, so we always have a complementary relationship when talking about percentiles. Okay. All right, on page 29, or sorry, slide 29, I just highlight the values to find the Z score. So we start with our Z alpha notation. We take 1 minus alpha. We look that value up inside the table, and then we come out to the axes to find the Z score. What's nice about this is that this is the only way of doing it. So that process is the same no matter what value you are looking for. Whereas with the areas, we have different tricks we can use to find the area depending on where we are under the curve and the value that, depending on where we are under the curve and which side of the value we want to be on. All right. Okay, so we'll look at 2 more examples. So we have in this question, find Z subscript 0.15 and Z subscript 0.6. Okay, so first we'll start with Z subscript 0.15. And then here we have Z subscript 0.6. All right, now just for clarity, based off of the previous discussion, this value here is the 80th percentile, or sorry, 85th percentile. Okay. Whereas Z 0.6 is the 40th percentile, right? So again, just that complementary relationship, a bit confusing in the context of what we are doing, but this is how the notation works. All right, so for Z 0.15, what we are going to sketch out roughly is where the value would be located. We don't actually know what the Z-score value is going to be, but we can use the curve to highlight where we think the value is going to be located. All right, so in this particular situation, we're going to start by marking just roughly where we think the value is going to be located. Okay, so we'll go right about here. So we have Z 0.15. Oh, that was weird. Okay, so this is a size of 0.15. All right. Okay, so step 1 minus 0.15 is equal to 0.85. Okay, so now all we have left to do is to look up 0.85 in our standard normal table. So we go to our table. We're looking for 0.85. Okay, so the closest value is right here. So you can see we have 0.8508 versus 0.8485. This value is clearly closer than the other value. So we come out to the axes here and we have 1.04. All right, so in this case, we have 1.04. Okay, in the second exercise, we're going to apply the exact same technique. The only difference is where our sketch puts the value. Now, in this case, we are being told that the subscripted value, so the area to the right, is 0.6. So that means that we have to cross 0 because there's 50% of the area on each side of 0. So in this case, we're going to sketch on the left side of 0. So maybe over here, for example, and our area is going to be everything to the right. Okay. So this is size 0.6. Okay, so our Z-score here is like that. All right, so same process as before. 1 minus 0.6 equals 0.4. Okay, so we go to our table. We're going to look up 0.4 inside the table. Okay, so here's the closest value, 0.4013. All right, so we come out to the axes and we have negative 0.205. Okay, so Z subscript 0.6 is negative 0.25. Any questions? So anytime, sorry, the question is, when do we know to use the negative table as opposed to the opposite table, as opposed to the positive table? All right, so for Z alpha, when alpha is less than 0.5, use positive. When alpha is greater than or equal to 0.5, use negative. That's basically how it works. So whenever the subscripted value is greater than a half, you would have to use the negative table because that means that you're crossing 0. Whenever the subscripted value is less than a half, that means that you're still on the positive side. So that would be a positive z-score. Does that make sense? Any other questions? Okay, so we have now seen the two basic or foundational trying to think of the right words here. We have now seen how to find area underneath a standard normal curve and how to find a z-score using area under the standard normal curve. So we've gone in two directions. Started on the axis, gone under the curve. Number two, started under the curve, gone to the axis. Now what we're going to do is take these two ideas and add in one additional step. So we have talked about how, or I mentioned briefly, and we discussed it, we sort of alluded to it last class, that there's an infinite number of normal curves. So for example, on assignment number 3, there will be questions where it tells you that you have a normal curve with some mean and some standard deviation, and they don't have to be 0, 1. They could be mean 4, standard deviation 6, or like mean 25.2, standard deviation 3.8. There's, again, an infinite number of normal curves because the mean and the standard deviation can be any real number. So the question then is, if we don't have a standard normal curve, if we just have a general normal curve, how can we still find area underneath that curve? And how could we still find percentiles of that normal distribution for any parameter set? Okay, well, the answer is we simply take the parameters of the normal curve that we are working with, we take the value that is of interest to us, and we make it into a z-score. And that's what equation 1 does. So equation 1 is our standardization formula. So what this value does is it takes any value of x, so any value on a normal distribution, and it changes it into a z-score based off of that normal distribution's mean and standard deviation. So effectively, if we are working with a normal curve that has any parameter set, but we still want to find an area underneath that curve, all we have to do is take the value that is of interest to us and change it into a z-score. Once we do that, everything is exactly the same as the techniques that we had just learned. All right, so for example, suppose we have a normal distribution that has a mean of 4 and a standard deviation of 2. Okay, so you can see an illustration of this distribution below. All right, so instead of being centered at 0 now, we are centered at 4. And the standard deviation is equal to 2. So if we were to compare this to a distribution with a standard deviation of 1, we just have slightly bigger tails and a lower peak. All right, we want to know the probability that x is less than 3. So here, we have x equals 3. So we want to know the probability or the area that is below x equals 3. Okay, so we just want to know this red shaded part. All right, so the first thing that we have to do is recognize that this is not standard normal. So the mean is not 0 and the standard deviation, sigma, is not 1. So what we need to do is convert x equals 3 into a z-score. So to do that, we use our standardization formula. So in step 2, you can see I have z equals x minus mu over sigma, which is equal to 3 minus 4 over 2, which is equal to negative 1 over 2, which is negative 0.5. Okay, so therefore, the probability that x is less than 3 when mu is equal to 4 and sigma is equal to 2 is the same as the probability that z is less than negative 0.5. Right? So we have just taken our general problem and changed it into our z-score problem, which we have seen lots of examples of. So now this thing here is going to be standard normal and we just want to find this red shaded part here using the standard normal table. Okay, so our z-score is now negative 0.5. So we go to the standard normal table. We look up negative 0.5. So that's right here. Okay, negative 0.50 in this case. And we have 0.3085. So that means that the probability that x is less than 3 when mu equals 4 and sigma equals 2 is equal to the probability that z is less than negative 0.5, which is 0.385. 0.3085, sorry. Okay. So in general, this process of finding area underneath any normal curve is exactly the same as the process of finding area underneath a standard normal curve. So the exercises that we started reviewing today and we finished off with last class. The only difference is that one additional step where you convert the x value into a z-score. After that, everything is exactly the same. Okay. Annalise, so will the sigma and mu numbers be given to us or will we have to figure them out? They will have to be given. I can't think of an illustration where they wouldn't be given because you need to know them in order to convert. So if you read the question, it should give it to you. Any other questions? All right, so exercises related to this problem. The substrate concentration of influent to a reactor is normally distributed with mu equals 0.3 and sigma equals 0.6. Okay, so what we're doing here is we're basically saying let X be substrate concentration. All right, so our variable of interest is capital X, which is the substrate concentration. X is normal with mu equals 0.3 and sigma equals 0.06. Okay, so we are then told that X is normally distributed with a mean of 0.3 and a standard deviation of 0.06. So we're given the key pieces of information to understand what X looks like. So we know that the substrate concentration will follow that normal curve. And that normal curve is going to be centered at 0.3. What is the probability that the concentration exceeds 0.25? Okay, so here's our normal curve centered at 0.3. We want to know the probability we exceed 0.25. So now we can mark down, just sketch out where 0.25 is going to be. So our middle point is 0.3. We're interested in X is 0.25. So we want the area to the right of 0.25. Okay, so this is what we are interested in. So the question is, what is the probability that X is greater than 0.25? Okay, so we need to convert this into a standard normal. There are two ways that we can write this out, but both ways are following the process from the previous slide. So step one is convert to z-score, and step two is just look the value up. We can write this in two ways. So you can either calculate the z-score first and then put it into the probability statement, which is what I did in example 1 on the previous slide. Or you can write everything within the probability statement. And that would look like this. So we have the probability that X is greater than 0.25 is 1 minus the probability that X is less than 0.25. Okay. This is 1 minus the probability that Z is less than 0.25 minus 0.3 over 0.06. All right, so what I'm doing here is I am converting to the z-score within the probability statement. So this is not different from what we did in the previous example. It's just a different way of writing it, but the process is exactly the same. So that gives us 1 minus the probability that Z is less than negative 0.83. Right. So now all we have to do is look up negative 0.83 within the normal table. So we go to the normal table. We look up negative 0.83. We match those values together, and that gives us 0.2033. right? So we have as our final answer. All right. Any questions? Okay, if there's no questions. Part B says, what is the probability that the concentration is at most 0.1? Same style of problem. It's actually a little easier because we don't have to subtract. So we start by sketching out our curve. We mark down where 0.1 is. And we want to be at most 0.1. Okay, so that means that we want to be to the left of 0.1. All right, so this question is asking, what is the probability that x is less than 0.1? This is the probability that z is less than 0.1 minus 0.3 divided by 0.06, which is the probability that z is less than negative 3.3. Actually, sorry, this for clarity is going to be 3 like that. Okay, so now all we have to do is look up negative 3.33 repeating. So we go to our normal table. Here's negative 3.3. Here's 0.3. And here's 0.04. 0.0004. All right. So that means that the probability that x is less than 0.1 is equal to the probability that z is less than negative 3.33, which is equal to 0.0004. It depends on the value you're looking for, Brooke. So I subtract, the normal tables are cumulative tables. So they always give us area to the left. So in general, if I want an area to the right, I would subtract from 1. Yeah, so the question is, what if we had to find z less than 0.55 repeating? Then in that case, it would be fine to round to 0.56. You can just obey standard rounding rules. Or actually, in that case, if you wanted to, you could average 0.55 and 0.56 as well. But technically, you're correct because it's a repeating value, so they would round up. So just obeying standard rounding rules in that situation is perfectly fine. Any other questions? Okay, so the last topic within the normal table section is the extension of the of finding percentiles. So the first new thing that we talked about today, where we had area under the curve, and then we wanted to find a horizontal axis value. So now it's the same idea. We're going to start with some area underneath any normal curve. And our objective is to find the X value that would give us that area. Now, in general, these types of questions usually present themselves as percentile questions, but theoretically, theoretically, you could ask for the area in any way that you wanted to. So the trick to this unit is just being able to identify what area you want underneath the normal curve of interest. Once you have figured out the area that you are looking for, we go into the normal table and we find the z-score that corresponds to that area. So the same thing that we did when we first learned how to find z-scores based off of area at the start of today's lecture. Once we have the z-score, we convert it back into an X value. So effectively what we're doing here is just the opposite of what we just learned. So what we just saw was how to find probability underneath the normal curve when you start from any normal curve, from any X value. Now we're starting with an area under the curve and just going in the opposite direction, essentially. So that would work like this. Suppose that we have a normal distribution that has a mean of 2 and a standard deviation of 5. And we want to know the 90th percentile of that distribution. All right, so we start by sketching the curve. Notice how So notice how this curve is centered at 2, okay? So we're at mu equals 2 in the middle because that's our mean. We're being asked to find the 90th percentile. So this barrier here represents a z-score with 0.1 to its right. So this white unshaded part here is a size of 0.1, and this red shaded part here is a size of 0.9, right? So percentiles are always from the bottom up. Our z-score notation gives us area to the right. So again, just like I had described before, it's a complementary relationship. So we want the 90th percentile. So that's going to be that's going to start with the z-score that has 0.1 to its right. Okay, so now that we have identified what we are looking for, what we need to do is look up the z-score that has 0.9 of the area to its left and 0.1 to its right. Okay, so that's this part here. So now we have a standard normal curve. Here's our z-score of interest. Okay. So this is a size. So just like the graph above, this is a size of 0.9. And this unshaded part is a size of 0.1. So we're going to look up So we're going to look up 0.9 in the standard normal table. This is, again, the same thing that we were doing at the start, the first thing that we learned that was new at the start of today's class. So we go to the table, we look up 0.9. So the closest we can get is right here. .28. Okay, so the Z-score that corresponds to the 90th percentile is 1.28, which is shown here. And now what we do is we just convert this back into an X value based off of the parameters of the normal distribution that we are working with. Okay, so we plug in X equals Z sigma plus mu. So that's 1.28 times 5 plus 2, which is 8.4. Okay, so the 90th percentile of the normal distribution with mu equals 2 and sigma equals 5 is 8.4. Any questions? Okay, so an exercise related to this problem. So we have the same setup that we had in the previous exercises. So we still have this influent or substrate concentration of influent. We have the normal distribution with mu 0.3 and sigma 0.06. How would you characterize the largest 5% of all concentration values? Okay, so what this question is asking us is, for this normal distribution, what X score bounds the largest 5% of values? So what X value has 5% of the area under the curve to its right? So if we were to sketch this, we would start with our normal curve. Okay, so this curve is centered at 0.3, which is our mean. This value here is the value that we are looking for. Okay, so we have from the question a size of 0.05. So it wants to know what value bounds the largest 5% from the rest. So we want to know what X value puts 0.05 in the upper tail. As a result, this part here is actually the 95th. This part here is a size of 0.95, right? Which means that this value that we're looking for is actually the 95th percentile, okay? All right, so to start, off, we just find the corresponding Z-score. So we want X subscript 0.05. So we start by finding Z subscript 0.05. 1 minus 0.05 is equal to 0.95. Therefore, Z 0.05 is equal to, so we go to our normal table. We look up 0.95 inside the table. All right, so 0.95 is that special value that's bounded in between these two numbers perfectly. So that means that it's going to be the average of 1.64 and 1.65. This is a unique value. This kind of averaging does not happen very often, but for this particular value, we would use this trick. Okay, so now we have Z subscript 0.05. So now all we have to do is convert this into an X value. So X equals Z sigma plus mu is equal to 1.645 times 0.06 plus 0.30, which is 0.3987. Any questions? So the question says, how would you characterize the largest 5% of values? Right? So the largest 5% of values would be the 5% of values that are in the highest part of the distribution. Does that make sense, Madison? Annalise, why was the last example such a big number compared to 0.3987? This distribution has a mean of 0.3 and a standard deviation of 0.06. In the previous illustration, the distribution had a mean of 2 and a standard deviation of 5. So they're completely different parameter sets. This standard deviation is much larger, so the result is a larger value. Any other questions? The formula Z equals X minus mu divided by sigma is for converting a normal value into a standard normal value. So it would not be for finding percentiles. This formula here, if you want to phrase it that way, X equals Z sigma plus mu, that would be for finding percentiles. Yeah, Tierra, sorry if I butchered that. So this number here, X subscript 0.05 is equal to 0.3987. That's true. Mackenzie, did you get the answer? Okay, cool. Any other questions? Okay. Okay, so there's one main topic left in this lecture set, which is on construction of the normal probability plot. So what is a normal probability plot and why do we need them? The idea here is that you might be given a data set and you would like to know if the data is normal. So maybe you don't actually have any information about where the data came from. You're just given the values and you'd like to answer the question, is there evidence that this set of values might belong to a normal distribution? The normal probability plot is our tool for answering that question. So it's a tool, a visual tool that allows us to determine if the data that we are working with gives evidence that the variable of interest belongs to a normal distribution. Constructing this table is actually quite straightforward. All you have to do is, one, count how many values you have. So just determine how many observations are in the sample. Two, order them from smallest to largest. Three, look up the corresponding z-scores in table 3, which is a new table that looks like this. Okay, so you can see in table 3 here, and this is also posted on Blackboard, the only variable is sample size. So we just need to know how many observations we have, which again, you just do by counting the number of values. Okay, and then you match your ordered values to the values from table 3 and you create a scatter plot. If the relationship is linear, we have evidence that the variable is approximately normally distributed. If the relationship is not linear, then we have no evidence to suggest that the variable is approximately normally distributed. Okay. All right, so let's look at an example and then an exercise. Okay, so suppose that you are given the following set of values. And the question is there evidence that this variable is normally distributed? Step 1, count the values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. N equals 10. Okay, step 2, order the values. Okay, so here under observed values, we have the order. So you can see that these values here are the same from the table above. They're just from smallest to largest. Step 3, go to table 3 and look up the corresponding z-scores. Okay, so we go to table 3. We have 10 observations. So we are just taking this set of values here. So notice that I'm literally just pulling this set of values out and I am placing it next to my observed quantities. So this here is from table 3, n equals 10. All right. The last thing I do is create a scatter plot. Okay, so this was step 2, step 3, step 1. Okay, so here's my scatter plot. I have the normal score on the y-axis and I have the value on the x-axis, but that honestly doesn't matter. You can put them on whichever axis you want, because if it's linear, it'll still look linear. Okay, so here, for example, this point is negative 1.55, 2.45. Okay, so this scatter plot is built in the same way as we had discussed at the end of lecture set 2. The last thing that I need to do is just check to see if this relationship looks linear. Okay. So to do that, I'm just going to sketch a straight line through the data. So here's my straight line. And then I'm going to say whether or not I think that this relationship looks linear. And in this case, I think that it's fair to argue that the points follow this straight line pattern fairly well. Certainly the bulk of the observations do. This guy here, bit of an issue. So we might ask, is this an outlier? Because it's a little bit off the pattern, but the majority of the points are quite close to the line. So because the relationship looks linear, we can say there's evidence that the variable is approximately normal, right? And that's all there is to it. So if we want to answer the question, is the variable that we are studying, is the variable that we are studying normally distributed? We can use the normal probability plot to answer that question. Jordan, what slide is table 3? It's not on a slide. It's a separate table. It's on Blackboard. It's labeled normal scores. All right. Any other questions? Because there's a mistake. That's why. Yeah, good catch, Kareem. It was an error. Any other questions? Okay, so I just want to go over an exercise of building the plot now. Okay, so we have the following sample. We're being asked to construct a normal probability plot and then comment on whether or not the variable of interest is normally distributed. So we're just doing what we did in the previous illustration, but I've broken it into 2 parts. Okay, so 1A, step 1, count the number of values. N equals 6. Oh, I should write that out, right? Step 1, N equals 6. Step 2, okay, so in step 2, we're going to order the values. So we're going to have 2.66, 2.98, 3.14, 3.45, 3.80, 12.56. So I'll do I'm going to write this as step 2/3 because I'm going to build our little table here. Okay, so step 3, we look up the corresponding Z scores. So we go to our normal scores. Here's N equals 6. So these are the values that we are going to use. So we're just taking this set of 6 values and placing them next to our observed quantities. So negative 1.28, or here, so negative 1.28, negative 0.64, negative 0.20, 0.20, 0.64, 1.28. All right, step 4, we construct our plot. Okay, so it doesn't matter which axis we put the scores on and which axis we put the observed quantities on. The relationship will be the same regardless of how we orient it. I'll just stick with the previous illustration. So this is going to be negative 1.5, negative 1, negative 0.5, 0. Actually, 1 second. I'm going to draw this a little differently. Okay, no, that's fine. I'll just keep it the way it is. Okay, and then here, we got to go from 2 to 12, 2, 4, 6, 8, 10, 12. Okay, now we have to mark the values down. So 2.66, negative 1.28 will be right about there. 2.98, 0.64 will be right about there. 3.14, negative 0.2 will be right about there. 3.45, 0.2 will be right about there. 3.8, negative 0. Or positive 0.64 will be right about here. And then 12.56, negative 1.28 will be way over here. All right. So then what we can do is draw the straight line. All right, so we can see that those initial 6 points here, those initial 5 points, they fall very closely to a straight line pattern. So in this situation, we can say the normal probability plot gives evidence that the variable of interest is approximately normally distributed with one potential outlier. Right. Okay, so right up to the wire. Okay, so that's probability plot construction. Again, pretty straightforward. We're just building a scatter plot, and then we're checking to see if the relationship is linear. I only have a few slides left from lecture set 5. They're just talking about basically like when we would note something as an outlier, but we have an example of that here as well. So on Thursday, we'll just finish that up. So a little bit of review of normal probability plots, and then we'll start lecture set 6, which is the lecture set on sampling distributions. It's actually quite small, and most of the techniques in it are based off of what we learned today when we're transforming into Z-scores. So we'll probably finish that on Thursday, I hope, and then we'll have everything we need for assignment number 3. But for the most part, you'll be able to do pretty much all of assignment 3 at this point, except for maybe the last question or two that are related to the sampling distribution. All right, so have a good week, or sorry, have a good couple of days. It's only Tuesday, and I will talk to you guys on Thursday morning.